so these are vectors, and our first vocabulary words are scalars and vectors. And the difference is that scalars are basically just numeric quantities, and the vectors add a direction to those, right? So the easiest example for me that most people tend to know is speed and velocity, right? Because speed plus a direction gets us the velocity. So let's go ahead and look at these examples and see if we can identify vectors versus scalars. So 5 meters is a vector or a scalar?
It's a scalar.
It's a scalar. There's no direction. What about 30 meters per second east? Vector has a direction. 5 miles north, also vector. 20 degrees Celsius, scalar. 4,000 calories, scalar. 256 bytes, scalar. 15 meters per second at 30 degrees to the horizontal, definitely a vector. We have a direction. The football player was running 10 miles an hour towards the end zone, vector or scalar? Vector, because we have a direction for how fast he's moving. So moving on, the next thing it asks us to do is take a look at figure A and identify some sort of definition for the initial and terminal point. Well, I mean, the initial point is just, the starting point or where it starts. And the terminal point is just where it stops. Stopping point. Because a vector has a direction and a length or a magnitude. Okay, and so for that reason, it's a directed line segment. So it doesn't just kind of go either direction. It has a specific direction. That's why the arrow is there. Right, then looking at B, it says, what do you think it means for vectors to be equivalent? There are 2 criteria. Anybody have one?
Going in the same direction.
They have to move in the same direction. And what's the other one?
Angle.
Angle is a way we describe the direction. Yes, I agree with that. / angle. A completely separate criteria. How else are these similar?
The same magnitude?
Same magnitude or length. So they must be going in the same direction and have the same magnitude to be considered equivalent.
Does magnitude equal size?
It is the length of the side, right? So the length of the side. So for example, let's say I was on a coordinate grid, and let's say I had a vector that was from the origin and here. So this length would be the magnitude m, and this angle would be the direction. Okay. And so this would be the direction of the vector, and the length of the vector itself would be its magnitude. So, like for example, you could say, if this length, let's give an example, if this length was 12, and this angle is 45 degrees, then you might say 12 miles per hour at 45 degrees above the horizontal. We had an example like that when we were naming vectors and scalars earlier, and these are the parts of that. Okay, so this is my direction. This is my magnitude or the length of the vector, which describes some numeric quantity, whatever it might be, whether it's speed or mass or anything else. Okay. So the magnitude of the vector is the distance between the initial and terminal points. So what are some ways we can calculate that? Well, you can use the distance formula if you like that. Or you can use, what we got the distance formula from, which is the Pythagorean theorem. You can construct a triangle where the hypotenuse is just the length of the vector. All right, so let's do a few. So we're going to calculate the magnitude of these vectors. I'm going to zoom in. And so basically, let's look at the vector EF, which is denoted EF with this half arrow above it. That is the proper notation for a vector. I would read this vector EF. What it is not is this. See how there are 2 little points on the arrow here? Shh. This is kind of a half arrow up here. So this is the vector EF. And the magnitude of the vector EF is denoted by two vertical lines on either side of the vector. So we read this, the magnitude of the vector EF. And so to do that, you could either do the initial and terminal points and do the distance formula. For me, I'm just going to construct a right triangle with hypotenuse EF. And this is a length of 2. This is a length of 8. And so by the Pythagorean theorem, we would just take the square root of 2 squared plus 8 squared. But so I could do that real quick. 2 squared plus 8 squared is going to be 2 root 17. All right, I got another one here. I've got vector AB. So we'll denote that vector AB. And I want to find the magnitude. So again, if you see these two vertical lines, that means it wants the magnitude. This would just be 6 and then 4. So that would be 6 squared plus 4 squared, bless you. Which would be 2 root 13. And then CD is a little bit different because it's not going in a positive direction. So this one would be, if we constructed this triangle, you'd end up with a vertical change of -4 and a horizontal change of +4. And so for the vector CD, now when you're finding the magnitude, that doesn't really change a whole lot, those negative numbers, because you're going to square them anyway. But later, when you're finding the direction, they are important. And when you're using the component form, they're important because if it's going up, it's a completely different vector than it's going in this direction. So this would be -4 squared plus 4 squared, which would be something. 4 root 2.
Can we put it in decimals?
Sure, unless it specifically asks for the exact value. All right, so are any of these vectors in the photo, or not in the photo, but in the diagram, are any of them equivalent?
No,
No, why not?
they don't have the same magnitude.
Right, they are not of the same magnitude. So no, they have different magnitudes. They also have different directions, but them having different magnitudes is sufficient for them no longer to be equivalent. So of the vectors above, only EF is in a standard position. That's this one. What do we think the standard position means?
Starting at the origin.
Starts at the origin. Exactly. The initial point is at the origin. And that actually makes things easy for us when they are in the standard position, because when it starts at the origin, the horizontal and vertical components are just the terminal point itself, right? So now it wants me to draw one that's equivalent to AB and in the standard position. So here's AB. Let me do it in green. And the horizontal component was how long? How many units?
6.
And the vertical component was how
4.
long? 4. So,
Stop that.
I just go over 6 and up 4, and then I have my vector in the standard position. This is equivalent to AB. It's AB again, except it's starting here. What's the terminal point now? What is it? 6, 4. So see how when we move it to the standard position, it's easy to see that this is 6 and this is 4. All right. Without drawing the vector on the grid, where is the terminal point equivalent to CD?
-4.
4, -4. How do you know?
Because
Well, because if this was 0, 0, I would go vertically down 4, and I would go to the right 4. And so I know that horizontal change corresponds to the x coordinate, and the vertical change corresponds to the y. So finding the terminal point of a vector in the standard position just involves the x is the horizontal change and the y is the vertical change, which is, not a new idea for us. We just did it with parabolas and all that. And so here's your big vocabulary word. A vector whose point is the origin can be represented by the coordinates of its terminal point. This is called the component form, and we write it in these sharp parentheses, where essentially it's x and y of the terminal point in the standard position. Basically, this is the horizontal change, and this is the vertical change from initial to terminal. Let's do this one. So here's this vector AB. It's defined by this terminal point AB in its component form. What are the values for A and B? So what's the value for A?
4, 0.
4, just 4.
Just 4.
Mhm.
Yeah, probably say.
And then what is the value for B? B is just 3 because this vertical change is 3. So this is 3 and this is 4. So notice we call it component form because we are writing the vector in its horizontal and vertical components, right? So the component form is 4, 3. So this is the horizontal change 4 units and the vertical change 3 units. So this is the component form of the vector that ends at that point. Okay, graph the vector in this component form 4, 7. Well, I mean, in the standard position, that's pretty easy. We just go right 4, up 7. And then draw the vector to the terminal point. All right, I can find the magnitude without counting because I already know that this is the horizontal and the vertical part of it. So I can find the magnitude of V, just by taking the components and putting them into the Pythagorean theorem, because those are going to be the legs, right, of the triangle. The horizontal one is 4 and the vertical one is 7. How can the magnitude of the vector in component form be found for any vector of this form? Well, it said, let's say we have vector v sub 1 comma v sub 2 in component form. Well, I can just take the square root of v1 squared plus v2 squared, because these are just basically the x and the y, right? This is your formula. You just take the horizontal component and the vertical component and throw them into the Pythagorean theorem. Here's another side question. How can I find the direction theta of the vector v? This was not something that you did, but I want us to do it. How can I find the direction? How can I find this angle? Any ideas?
Tangent -1 b over a.
Yeah, let's do, we can say the tangent of theta is the opposite over the adjacent. And then to solve for the angle, I'll just take the tangent inverse of that ratio. This is throwback to trig again. All right, so the tangent inverse of 7 over 4 is going to give me 60 degrees. So the direction, so the magnitude of the vector, we found that. It'd be 4 squared plus 7 squared, so the magnitude is root 65, and the direction is 60 degrees. So this is O and this is A, but I could also just call them, plain old y and x, right? Or I could call this V1, V2, or V1. Whatever. However your brain likes to think about it, it's all the same thing. The bottom line is you can go directly from the component form to magnitude and direction without a graph. Just by understanding that this is essentially horizontal and vertical, using the Pythagorean theorem for the length and using the inverse tangent for the direction, since that uses the horizontal and vertical. Works that way every time. All right, so find the component form and the magnitude of the vector that has the initial point 4, -7. Well, this is unfortunate because this is not in the standard position. This would be 4, -7, and -1, 5. So that would go right down through here. Well, you could always use the graph and count, but really all we're interested in, let's say this is the -1, 5, and this is 4, -7. Remember, a vector in component form is the horizontal and the vertical change. Well, that's just the differences in the x's and the y's, just like we've been doing with the parabola, right? So if I go from here all the way up here, what is the change? Did I write those coordinates down wrong? 4, -7. So what is the horizontal change between these 2 points? Well, it's just -1 minus 4 equals -5. And then, so what's the vertical change? Well, that's just 5 minus -7, which is +12. Which makes sense because if you draw this triangle and count it, you'll see that that's 12, and this is -5. But this works too. Essentially what we did is we took the terminal point and subtracted the initial point. So now let's do that in general. If this is the initial point and this is the terminal point, then what's the component form? Well, we just said that we were going to do terminal minus initial. So let me kind of write that down here. And these would be your x's, right? So that's these. So it'd be u1 minus v1. And then these are your y's. And so it would be u2 minus v2 in general. Basically, you're just subtracting x's and y's to get new x's and y's. Questions so far? Just kind of refining what you hopefully were able to get out of that. But I want to do one example from the delta math with you. And so the second part of the delta asks you to, here's the original vector. What is the component form? Well, this would be -4 and 3. Because remember, the component form is just the horizontal and vertical distances. To find the magnitude, I just take the component form and plug it into the Pythagorean theorem. And that'll give me the magnitude. And then finally, remember the direction is the tangent inverse of the vertical over the horizontal. Well, this is going to give you something tricky. So let's do the tangent inverse of 3 over -4 and see what you get. You'll get -37 degrees. Well, if you remember from the previous unit, tangent inverse in your calculator gives you, a value over here. What quadrant would this end up being in if this were an angle that started right here? at 0, 0. It'd be in quadrant 2, which makes sense because where's the hidden value for tangent? It's 180 degrees away. So we add 180 and you'll get your direction. Negative 37 plus 180, that should be 143 degrees, which if this was the horizontal here, if we moved it, which we would do, that would make sense, right? Because this is 90, so this whole thing is 143. So you'll have to call back up a little bit from the previous unit from the trig test. But it's just tangent inverse every time, so it's just going to be adding that 180 to it, depending on what